There's a mysterious three-sided section of the Pacific Ocean about 60 miles south of Tokyo, the Dragon's Triangle. There are thousands of stories and legends about the Dragon's Triangle, stories with just enough mystery and pseudo-fact to encourage widespread belief among conspiracy theorists. Lots of people believe something in that region causes planes to crash, ships to sink, and all kinds of other unexplained phenomena. Some nautical charts even go so far as to mark it a danger zone. In the software industry, we have our own equivalent of the Dragon's Triangle, a balancing act that software managers have to perform to accomplish a project plan while trying to meet all of the demands and constraints that have changed and been placed on it. Some unreasonable constraints, which are shockingly common, are setting delivery schedules and budgets without developing a detailed design, estimating without input from the development team, and a lack of recognition of the relationships between cost, schedule, and features. Our industry's Dragon's Triangle is composed of three elements: scope, resources, and schedule. A significant number of software projects disappear, fail that is, when they encounter the interrelated problems that make up software's Dragon's Triangle. A lot of software managers look longingly at other industries where life seems simpler and more predictable. I'd be lying if I said I didn't occasionally suffer from a little the grass is always greener disease myself. The industry that usually gets looked at first is construction, both something simple like building houses and large-scale construction like skyscrapers and sports arenas. To an outsider, it seems pretty straightforward. You have a set of requirements, the customer's expectations are set early on and are relatively easy to manage, a blueprint is developed before firm estimates and schedules are made, you're dealing with physical principles and construction practices that have been developed and refined over thousands of years. The subcontractors do their thing, you finish close to the promised deadline and within cost, and you make a profit. What could be simpler? Anybody with construction experience is having a stroke right about now. They can tell you that it's never that simple. When a construction firm bids a fixed price on a job, it's often to build something that no one else has ever built. That makes estimation something of an art. Experience and intuition take precedence over science and engineering. Bids are made so if there isn't a single change to the original blueprints, the contractor won't make a profit. The original bid covers only cost and labor. This strategy depends on the fact that it's just about guaranteed that there are going to be changes to requirements and blueprints. The profits lie in making and charging for those changes. Plenty of contractors openly admit to the practice, since they consider it massively risky to bid a fixed price on a job they've never done before, where they don't know what to expect. In software, it feels like we're always building something new and different. You might not think so when you're working on your 8th order entry and inventory control system, but trust me, they're all new and different in some way from their predecessors. Like the ancient Roman architects who built new cities on top of old ones, you might be building these new software systems on the ruins of older ones, or at least making use of the lessons learned with the old system. But there are some real and significant differences between building in the physical world and building in the software world. One big difference is our understanding of the problems we'll face in successfully completing a software project. In complex software systems, and I have yet to see one that isn't complex, the problems we face are only understood in broad terms. This is partly because of the complexity we have to deal with, but also because of our limited understanding of the interactions between the various components of the not yet built software system. We don't know the full ramifications of what has to be done until later, when the details are addressed. The newness and the opportunity for a software development team to do it right this time motivates the team, but it hides the level of complexity we end up having to deal with. Objects in the physical world have attributes that we experience with our senses. One problem with software is that it's an abstraction. It lives in a place that we can't experience with our standard 5 senses. It has properties that make it different from what we experience in the physical world. This table lists just a few. Not having other experiences to guide them, the software manager and development team members usually revert to what they've experienced in the physical world. It's like our learning takes place in one domain, while our actual work takes place in another. In the physical world, whether we're building a jumbo jet or a house, we can see, touch, and experience the results of the process. If we're satisfied that we're making sufficient progress, our anxiety level goes down without the use of pharmaceuticals. Digging a foundation, pouring concrete, framing walls, and so on are steps in a process that will lead to a complete house. These steps happen sequentially. Their completion indicates real progress that we can experience and evaluate. But if we're developing software, all we have to show at the early stages are, hopefully, some documents stating what the requirements are, an assessment of the cost and schedule, an architectural design, and so on. Until some form of the software is available for testing, we don't really have anything to experience. Software takes a giant leap of faith by the customer, the project manager, and everyone on the development team. They all have to mutually believe that the process being used, the means of documentation, and the content of regularly scheduled status reports can be trusted, and that proper progress is being made. But as we all know, there's nothing like a little reality to destroy a great theory or illusion. In general, engineering in the physical world has a better track record of anticipating problems and planning for them. For example, the engineers of the new international airport in Hong Kong anticipated serious settling and shifting problems because the airport was built on gravel that was just dumped into Hong Kong harbor. They took the problem into account and keep the runways flat through an elaborately constructed set of systems. So why is this sort of planning difficult in software? One major reason is physics. Engineers dealing with the physical world are working with immutable laws of physics. The laws of physics haven't changed since the Earth was formed. That makes it predictable. A runway built over fill material is going to settle. This can be experimented with, measured, documented, and planned for. It's much more difficult to deal with the future if you're producing software, where unforeseen problems or changes in the business climate can cause major setbacks, often in a matter of hours. In software, there's a lack of principles that you can use to plan for and prevent problems. There isn't a software manager alive who hasn't been faced with a scheduling, cost, or feature problem at some point. Maybe the project has spent well above the expenditure projections, or the project is behind the timeline that was established, or not all of the features are going to be present in the production system. In the real world, software managers usually get forced into dealing with all three of these problems at once. The Dragon's Triangle of software. Far too many software managers have wandered into this set of issues and been unable to find their way back out. The triangle's 3 points are made up of the requirements, functional, performance, strategic, and legal, that the system has to fulfill, the money, people, and skills used to complete the project, and the flow time allocated to the project, at the end of which a product has to be usable, or at least commercially viable. There are some unpleasant truths about the triangle. The first is that all three aspects of the triangle are interrelated. For example, you can't change the scope of the project without having to address changes in resources and schedule. Failing to do so guarantees that your project will fail. Adding people to a software project doesn't help as much as you might think, and there's plenty of research proving that it can make a project that's behind schedule even later. If you double the number of people working on a project originally estimated to take 1 year, it only knocks the flow time down to about 9 months. With software, there's definitely a law of diminishing returns. If you tripled the size of the team, you might get the completion time closer to 6 months. But then other issues, like cost, synchronization, availability of computing resources, and so on, come into play. Some efforts just can't be compressed or reduced beyond a certain point. You can experiment and try to find that point, but that's expensive and risky. Thirdly, no matter how much we wish we could, there's no realistic way to make the calendar march past more slowly. Okay, so you could shoot your development team off in a near light-speed spacecraft and take advantage of space-time field distortion theory, but the cost of that solution kind of defeats the purpose of this whole conversation. And finally, the feature list usually increases, a phenomenon we call feature creep, during the course of a project, rather than decreasing as the project becomes better understood. All of these sad truths have a negative impact on software team morale, because the team experiences a growth in the size of the job, without a corresponding change in schedule. Hiring people to help with the project just makes things worse, since they need significant help from the rest of the team to come up to speed. Just as an interesting data point, this table shows the differences between how issues related to scope, resources, and schedule are remedied in the hardware and software worlds. Notice the prevalence of death march mode on the software side of the table. The term death march mode refers to the practice of going all out on a project to finish it, resulting in 18 20-hour workdays, 7 days a week. This is a failure on the part of the software manager. Only startups should be working these kinds of hours. Death march mode happens when a software manager's experiences in the physical world cause them to treat the problem of software development as a deterministic problem. Here's an example of a simple deterministic problem. We need to haul a giant pile of dirt from point A to point B using wheelbarrows. Points A and B are within easy walking distance of each other. If we add more people with wheelbarrows, or work to people we have for longer hours, the job is going to get done faster. But even in a simple problem like this, there are plenty of scaling problems: fatigue, having so many workers they get in each other's way, and so on. Similarly, in software, mental fatigue sets in quickly in death march mode, productivity plummets, and the error rates increase. More importantly, in software, the problems just aren't deterministic. For example, tracking down a defect and correcting it definitely is not deterministic. There's no realistic way to know exactly how long it's going to take. One viable strategy to overcome cost and schedule overruns is to cut features, but this has some negative side effects. Unlike building construction, where a team of people addresses a number of features, in software there's usually one or two developers that are responsible for a feature. Cutting that feature can have serious impact on the morale of those programmers, as well as the team as a whole. In software, developers pour their heart and soul into their work, so they'll closely identify with the features they build. Having it deleted from a release, even if it'll be part of a subsequent release, is disheartening for the developers and might actually cause them to leave the project, or even the company. Assuming that the features more or less work, if you're the software manager on an effort that has to cut features, it's a good idea to meet with the team members who authored the features that are going to be cut and reassure them how much their work was appreciated. Make sure they understand that cuts reflect scheduling reasons, not their skill level or the quality of what they produced. A couple decades ago, the design theorist Ernst Riddle proposed the existence of a class of particularly troublesome problems that he labeled wicked problems. Basically, a wicked problem is one that's particularly elusive. When you try to solve it, other problems, or previously unknown aspects of the original problem, they become known and they present an impediment to finding a solution. Basically, it's quicksand. The more you thrash at the problem, the worse it's going to get. I think software development fulfills all the criteria of a wicked problem, and it's worth exploring those criteria. So, a wicked problem can't be definitively stated. Whenever we try to bound a software project using something like a specification, the requirements change, often in unpredictable ways. There's no rule or guideline to determine when a wicked problem is solved. In the physical world, there's generally a reasonable stopping point when you're generating solutions. For example, how much a bridge will flex under stated dynamic or static conditions can be computed using basic civil engineering principles. You can independently verify the answer, and the problem solved. But in software development, the only stopping points are when you run out of time or money. Wicked problems have only good or bad solutions, not right or wrong ones. Going back to my civil engineering example with the bridge, there's a range of answers that are correct, and everything outside of that range is wrong. Compared to software, that range of correct answers is very narrow. In software, there can be thousands of solutions that meet the specifications, which makes them good by that standard. Presumably, solutions that don't fit a specification are bad. A wicked problem cannot be definitively tested. This seems reasonable for software. If there aren't any right or wrong answers in the wicked problem space, there shouldn't be any way to accept or reject the solution in an analytic or scientific way. The one exception in software is whether the solution meets the specification, but even specification issues tend to be pretty arguable, and there's usually not a clear right or wrong. Solutions to wicked problems are too significant to be experimented with. Although the Department of Defense sometimes has aircraft companies create prototypes for a fly-off competition before they award a contract, building multiple software systems and selecting the best among them is prohibitively expensive in both time and money. Neither the number of possible solutions nor the means of distinguishing among them is limited. Software development is at least this wide open. Each wicked problem is unique. If you don't think this applies to software, try to count how many email clients or inventory control systems have been built worldwide. Issues inside of wicked problems are usually symptoms of higher level problems. If we're building a real-time system to process images from an MRI machine, and it's too slow, it might mean that we're using a processor that's too slow. The processor might have been picked to keep the cost down. QED, the performance problem could actually have been a symptom of a lack of funding for the project. So is software a wicked problem? I think it definitely is. Dealing with these problems isn't strictly a technical endeavor. It requires more of an empirical approach from managers. Successfully coping with software's Dragon's Triangle involves using what we know now, employing the data that's been gathered, and having the faith in those results to use them despite the conventional wisdom some managers employ. The non-physics based, and therefore almost mythological nature of software's Dragon's Triangle represents a danger zone that all software projects have to pass through. But a number of self-generated myths also threaten software projects. These myths are conceptual and are unfortunately held to be self-evident truths by many software managers. Myth number 1. Software is easier to change than hardware. This myth is more common and more counterintuitive than most managers care to admit. At first glance, changing software looks a lot easier than changing hardware. For example, how easy would it be to change the Hoover Dam? Not very. That's exactly why so much effort went into designing, analyzing, redesigning, and reanalyzing the structure before a single batch of concrete was mixed and poured. Considering the amount of planning that went into it, it's not surprising that the Hoover Dam finished ahead of schedule and under budget. It's still considered one of the greatest feats of engineering in the history of the world. So what about software? The problem is that we take the ease of change issue for granted. We see solutions early on, and then we start programming without really understanding the problem we're trying to solve, without looking to the future. The Y2K problem is a perfect example. Software teams just didn't realize that software they built in 1980 might still be in use by the year 2000. At the time, they were pretty pleased that they'd saved memory and storage space by condensing a 4-digit number down into 2 digits. If somebody had bothered to look around a little, they'd have realized that a lot of software still in use in 1980 had been written in the 60s and 70s. At least at the time, it was way too expensive to completely replace it every 20 years or so. Myth number 2. Maintenance mode doesn't need processes. We're in maintenance mode, and it's rare that we write something new, so we don't need to measure what we're doing, gather statistics, or define processes. So that was actually said by the director of software engineering for a major division of a Fortune 500 IT company at an industry conference. Obviously not this one. Such a lack of knowledge of the software business is, unfortunately, not unusual, even among people who really should know better. It's not exactly a surprise that the software produced by that division is of notoriously poor quality. This attitude is a tough one to overcome, since it has so many obvious cost-saving aspects. After all, why do something you don't have to do? This approach fails to learn some valuable lessons from the physical world. If you ever get a chance to talk to someone who works in the aircraft maintenance business, they'll tell you that they have formalized processes for everything they do. Consistent with FAA requirements, they gather statistics on every airplane they touch. They keep track of who worked on what plane, what they did it with, for example, what solvent was used, who manufactured it, and so on. If there's a failure, it's easy to see who the last person was that worked on the plane and fiddled with the failed system. This detailed process lets maintenance organizations continually improve the quality of their results, reducing failures while reducing cost. Managers who believe in this myth are major stumbling blocks to bringing about change in an organization and improving the quality of maintenance results. The director of software engineering I mentioned earlier ran a shop where there was no accountability, serious bugs would go unfixed for months and years, and everyone did their own thing. It was laissez-faire programming. The problem is that without metrics, processes, and methods, costs rise, quality suffers, and everyone loses, especially the end users of software. Myth number 3. We don't need to document our source code because any proficient programmer can tell what the code does by looking at it. Really? Anybody who says that has never experienced the very special hell of trying to understand 30-year-old code with nonsensical variable names. This practice burns up a lot of resources, which in turn affects the other points of software's Dragon's Triangle. This myth is so closely held by some people that they actively remove the ENCODE documentation from any software they work with. One programmer I used to know who actually did this was confronted by her colleagues and asked, not too politely, what she thought she was doing. Her response was, why bother putting in documentation when it's going to be out of date really soon anyways? By deleting the documentation, I'm actually saving us a lot of effort since we won't be misled by what we find. Her argument doesn't make much sense when you consider that personnel turnover can cause massive communication and productivity problems. Usually, you can prevent this problem with a simple requirement. A programmer has to make sure ENCODE documentation is updated and correct before checking in any changes. Some programmers and managers assume that this results in longer, more expensive development time, but nothing could be further from the truth. Following practices like this not only ensures the code is maintainable, but also gives flexibility in job assignments. Generally, it's a good idea to have quality assurance do a little spot checking just to make sure everyone is making a good faith effort to keep the documentation accurate. Myth number 4: quality can be tested into our software. What we should do is get it coded as rapidly as possible and then test it as thoroughly as possible. Rightly or wrongly, Henry Ford gets the credit for creating the first modern day production line. Believe it or not, he got the idea from visiting a slaughterhouse. The concept of quality was built into Ford's production model. He broke a process down into small steps, execute each step efficiently and perfectly, with quality inspections at key points along the way. The resulting system produces a high quality product at a lower cost. The other side of this myth is demonstrated by how Japanese industry operated before and after World War II. Before and during the war, the attitude in Japanese industry was that labor is cheap, so just build as many units as you can and then test them and ship the ones that work. Once Japanese industry underwent its post-war makeover, Japanese products have become revered for their quality. The correct attitude towards testing is that it only reveals if quality is present or absent. It doesn't actually increase the quality of a product. In today's marketplace, quality products at least have a chance of being successful. Those lacking quality are doomed to the scrap heap. Myth number 5: why bother performing analysis and design? After all, the code, not these preliminary documents, results in a marketable product. Subscribers to this myth don't really understand the roles that analysis and design have played in engineering for more than 2 millennia. There's plenty of evidence that the ancient Roman engineers built models, drew the equivalent of blueprints, and otherwise prepped a project before executing it. Rather than just building an aqueduct based on a few observations and the availability of slave labor, they ensured success by doing the math, measuring, estimating, analyzing, and otherwise working the project through in many ways before they committed to laying the first stone. What analysis and design actually do for the development team is get everyone synced with what'll be built and why it'll be built in a particular way. If you have a well thought out design in hand, one that's been walked through and agreed to by the development team, you're much more likely to succeed. Myth number 6: we don't need a quality assurance group. We hire smart people and they don't make mistakes. Most of you, well, maybe not all of you, would be surprised at who said that. Let's just say they used to be the head of a large software company whose products aren't always known for their quality. The quality assurance group's function isn't just to test software, it's to make sure that errors don't find their way into the software to start with. It's QA's job to establish a system of processes, checkpoints, procedures, guides, whatever it takes, to reduce the number of bugs in the code to the point they're traceable and manageable. Ideally, the QA team can make adjustments to processes and procedures to prevent bugs in the future. Myth number 7: increasing their compensation gets software professionals to perform at a higher level. This isn't always the case. In fact, it might actually encourage them to leave the company. According to recent research, there's a better than 50-50 chance that an employee will leave a firm within 3 months after receiving a raise. To be clear, I'm not saying that outstanding performance shouldn't be rewarded. Quite the contrary. But when people are putting in long hours, frequently telling a manager that they need additional help or some relief in the schedule or something to get their life outside of work back, they often get ignored. When the situation is going on and the person gets a raise, the company is sending the message that they're pleased with how things are going. The raise implies that the situation isn't going to change, so the employee feels that they have no choice but to leave the company. On the other hand, if the employee sees that it's a short-term situation, the outcome might be very different. Myth number 8: the best way to encourage people to get into management is to give them special perks. Definitely the wrong incentive scheme. If people go into management for the money and perks, we end up with what we have today. Software managers who would rather be programming, are uncomfortable dealing with personnel issues, do not understand what they're supposed to do, and are, in a word, miserable. This myth also requires some changes in corporate culture. An employee's pay should be a reflection of the company's perception of that person's value. There isn't necessarily a correlation between position and pay. Instead, forward-looking firms have a policy that it's possible for a manager to be paid less than the people who report to her or him. Myth number 9: software processes are great, but when the project is behind schedule, we don't have time for such things. It's been my experience that projects fall behind schedule precisely because the development team didn't follow some predefined process, or they took following it to the extreme. It's a delicate issue. What you need is balance. More often than you'd expect, you'll find that a software manager is ridiculously enthusiastic about a development process he learned in a course that the company spent thousands paying for him to attend. He follows the process to the letter, regardless of if the process makes sense for the project, the company, or its customers. This is how teams get into trouble. Remember that the guy who writes a book or teaches a course isn't going to have his career hurt by a failure. You are. An alternative way to look at this is that a process isn't worth using if it can't be used in an emergency. There's an abundance of research that indicates processes that can be used in an emergency have been credited with saving the day in a number of dire circumstances. In other words, effective processes are ones that have evolved over time to be effective in both ordinary and extraordinary circumstances. This is actually a pretty common situation in other industries. For example, on occasion Boeing gets an emergency order for a critical airplane part from an airline. The airline's plane can't be flown until the part is installed, but Boeing doesn't have one on hand. Boeing has a process that doesn't skip any of the inspection or quality control steps, meets FAA requirements, and gets the part into shipping in record time. The concept of streamlining a process when an emergency situation occurs, without skipping any of the steps, is one most software managers have yet to embrace. Myth number 10. The marketplace requires that we get to market as quickly as possible. Using some sort of prescribed method or process is just going to slow things down. There is some data to support the first part of this myth. Depending on which industry study you believe, the company who's first to market with a product targeting a specific segment can expect to lock up between 60% and 80% of that segment. By lock up, I mean that it'll be very expensive for the competition to perform a rip and replace of the first firm, probably more than the amount of revenue they can expect to see over the first 3 years. The second part of this myth is another matter. It doesn't take months or weeks to put together a well thought out process, maybe a few days. You don't need to be a genius to figure out that having a defined process with an execution plan, milestones to hit, and quality targets supported by checks and balances to reduce the number of bugs should take less time to execute than the Oklahoma land rush mode of development suggested by this myth. Myth number 11. There's so much software out there that's already included in development environments or can be licensed inexpensively. We can depend heavily on that and write very little new code. It's a nice idea, but I've never seen a case of it working out for commercially successful software. Commercial off-the-shelf, or COTS, systems are written for a particular user model, a specific class of application capabilities, and other commercial considerations. People want some form of uniqueness in the software they're paying for. If the software is the same, or close to the same, as other products, they're going to ask why it was built in the first place. In interactive systems, there are some pretty serious performance and response time issues that can be associated with using some popular COTS systems in production environments. Finally, integrating COTS packages from different authors is a major challenge and cost center. Myth number 12. If we institute processes in this organization, people will either leave the company or become unproductive. This myth is a long-standing argument against change, any change, usually voiced by managers who don't really have a clue about what can be achieved and what's going on in other software companies. It turns out that instituting processes and procedures into a software organization can dramatically increase morale, with commensurate increases in productivity and quality. There's plenty of data to back that up. When you hear about a process-induced failure, the story you're hearing is lacking a lot of detail. All you hear is that they tried this method or that and had problems. If you dig deeper into these situations, you'll almost always find that the software manager got scared because code didn't start immediately rolling out the door, panicked, and directed that the procedural approach be abandoned and coding begin immediately. Maintaining control over any part of a project is difficult, but controlling the schedule is probably the most difficult of all. Why? Because we can always get more money, reduce features, buy faster computers, and use better software tools, but we can't stop the clock. Many software projects fail miserably because of late delivery, or even no delivery. Postmortems on these projects usually reveal that management didn't fully comprehend how far behind the schedule the project was until it fell behind by some atrocious amount that they just couldn't overcome. What you almost never hear is that a project got behind schedule because it was attacked by Godzilla. What I mean by that is that the schedule slip wasn't due to a single catastrophic event. Instead, the project died because it was bitten to death by ducks. I have to be honest, I'm not a huge fan of ducks. They've chased me around parks since I was a little kid, and they still do. But trust me, if you've ever been nibbled on by a duck, it's pretty obvious it's going to take a lot of them to kill you. If somebody was nibbled to death by ducks, it would be pretty tough to pin their death on one particular duck. If you're managing a software project, every time somebody doesn't meet their commitments or misses delivery by a day or more, that's a duck. If enough ducks show up, the project is doomed. Small schedule slides can occur every day, and they can add up to a very large slide that jeopardizes the entire project. Although it might sound like a daunting task, successfully managing software projects is relatively simple. All you have to do is successfully navigate software's Dragon's Triangle. While that's easier said than done, it involves recognizing that software management isn't an exact science with right or wrong answers. There are three things to always keep in mind. Much of what we learn from the physical world in our everyday lives doesn't apply to software management. Quality affects more than just a product. It also affects the performance of the people producing the product. And if you aren't careful, small slides in a schedule can build into an avalanche that can't be overcome, no matter how hard everyone works.